If you can appreciate and accept this, we will now say that S is equal to R times theta, and S is an arc length. So just understand that it's a length. It's where the tire or where a wheel will meet a road. And so it's going to be like you can roll this tire and it has to complete a circumference, and that circumference will lay out on this road. How can I say it? It'll lay out on this road. All right, so that length is equal to some linear length. It's the same thing, but it's around in a circle. So here we go. Since we know that, we can look at the tangential velocity here. And I call it tangential because it's the velocity that's tangent. If your tires are rolling or moving, they need to have the same rotational, how can I say, tangential velocity as the velocity of the car. Or you're skidding, when I say you're skidding, you're braking, or you're burning rubber. I mean, the tire's going faster, the velocity, the tangential velocity is going faster than you're actually moving in the car. So you're burning rubber. Sometimes it might be good, sometimes it may be bad. But so let's define that. We know that delta S over delta T is just going to be the same thing as the tangential velocity. Okay, so let's define delta S real quick. Delta S is going to be delta R times theta. Now, how are we going to treat this? I believe this is called the chain rule. It's from calculus or from math, but I'm just going to say, well, what we want to do first, we're going to say R delta theta plus theta delta R. Okay, we look at the change, we hold one thing constant and then look at the change of the other variable, and then we hold the other variable constant and look at the change of the next variable. So in this particular case, our variables are R and theta. In this case, we don't want R to change. What is R? This is R. We want R to remain constant. If it remains constant, delta R is going to be 0. So that means that this piece goes away. So now we have a delta S. We have our delta S here equals to R delta theta. If we put delta S over time, we're going to, and we know that this is just the tangential velocity, we're going to end up with R delta theta over time. So what we call this, we say VT is equal to R omega, where omega is the angular velocity. And I'm not putting these vectors over this thing like I need to, but they are all vectors here. So this is delta T, the angular velocity. Angular velocity, all right? And so we're going to be using this equation. We're going to find our tangential velocity using Pythagorean's theorem. Basically, we have values for x, y, x velocity, and y velocity. So we know that we have x, we have y. We can find r using Pythagorean's theorem. But we also have, if I just can draw this, we have ourselves a tangential, or I want to say tangential, yeah, tangential velocity, and it's just going to be made up of Vx and Vy. And we're going to again use Vx squared plus Vy squared. And once we do that, we can determine what our angular velocity is, because we know that that's just Vt over R. If we go back, you'll see that that's the definition of, that's our definition of angular velocity. VT over R. I just rewrote it. That's all. I just did some mathematical stuff there. Okay. We're also going to look at the angular acceleration. And I'll talk about that in a little bit.